So now we're going to practice hybridization, and before we get started on these problems, I am going to show you a trick that I use for hybridization. What we're going to do is write up the number of each different types of orbitals. For example, in any energy level, there's one s orbital. There could be as many as 3 p orbitals. There could be as many as 5 d orbitals. We're just going to keep this little trick handy. Hybridization is referring to the number of s and p and d orbitals that have to get mixed together for this atom, or for this molecule to be formed. And in order for us to determine hybridization, we actually need to be looking at Lewis structures for these molecules. So I'm going to draw the Lewis structures really quick on the side, so we'll have them handy as a reference. I'm going to be leaving a lot of things off of them. Like, for example, I'm not going to take the time to draw lone pairs on the outer atoms because it actually doesn't matter when we're talking about hybridization. When we're looking at hybridization, we just really want to focus on the central atom. It's actually directing us to that in the problem. And we are looking specifically at how many areas of electrons are around that central atom. That could be a lone pair, it could be a double bond, it could be a single bond. This molecule has 3 areas of electrons around the central nitrogen atom. If we need 3 areas of electrons, that means we need 3 orbitals for hybridization. I'm going to change this color. And so what we're going to do is just count. If we know that we need 1, 2, 3 areas of electrons, how many orbitals does that correspond to? That corresponds to an s, and it corresponds to 2 p orbitals. So the hybridization for this guy is going to be sp2. They always move in order from left to the right, the way that it's written now, because this is the low energy and this is the high energy, and we always put these orbitals together in order from low to high energy. So now what I'm going to do is redraw. I'm going to shift to the second molecule, which is NCl3. And there is a lone pair of electrons on that central nitrogen. In order to make this molecule, how many areas of electrons do we need? We need 1, 2, 3, 4. 3 bonds and 1 lone pair. That means we need 1, 2, 3, 4 orbitals. That's going to be an sp3. It really is this straightforward. If we want to do this for H2O, I'm just going to modify this a little bit. H2O looks like this. We want to look at the central atom. How many areas of electrons do we need? 1, 2, 3, 4, just like the previous example. That's going to be sp3. Next we have SF4, and that Lewis structure, again, I'm leaving out a lot of lone pairs. That Lewis structure looks like this, and we only need to look at the central atom. We have 1, 2, 3, 4, 5 areas of electrons. We need 1, 2, 3, 4, 5 orbitals. That's going to be s, 3 p's, and a d orbital. For IF3, I'm just going to get rid of a little bit of this. For IF3, it looks like this. And we've got 1, 2, 3, 4, 5 areas of electrons, which means we need 5 orbitals, sp3d. And for I3 minus, that molecule looks like this. Again, that's another 1, 2, 3, 4, 5 areas of electrons. It's another sp3d hybrid. Now we have our last two. We have XeF5 plus, which looks like this. And focusing on that central xenon, we have 1, 2, 3, 4, 5, 6 areas of electrons, which means we need 6 orbitals. 1, 2, 3, 4, 5, 6. That's an S, 3 P's, and 2 D's, sp3d2. And if this was XeCl4, then our Lewis structure would look like this. Still 4 areas of electrons, 1, 2, 3, 4, 5, 6. That's also sp3d2. So now we're going to practice the same thing. I'm going to move this little helpful trick down here. We've got a molecule all drawn out for us, and we're going to determine the hybridization of every atom except for hydrogen. So let's start with this carbon right here. If we look around the carbon atom, there are 2 areas of electrons, which means it needs 2 orbitals. So this carbon is sp. And the carbon that's next to it also has 2 areas, needs 2 orbitals, so that one is also sp. This carbon right here has 1, 2, 3, 4 areas. It needs 1, 2, 3, 4 orbitals. That's sp3. So I'm going to do it like that. This is sp3. The carbon, if we're continuing down the chain, next carbon over, this one has 1, 2, 3 areas of electrons, so it needs 3 orbitals. That's sp2. And let's keep going in that same direction. So now we have this oxygen atom, which has 1, 2, 3, 4 areas, 1, 2, 3, 4 orbitals. That is sp3, and we have one more to go, this last oxygen atom up here. This has 1, 2, 3 areas, 1, 2, 3 orbitals is sp2. This is also asking us to count how many sigma and pi bonds we have in the molecule. Every single bond is a sigma bond, so I'm going to highlight them. We have 1, 2, 3, 4, 5, 6, 7. In addition to that, every triple bond has 1 sigma bond, so there's number 8, and every double bond also has 1 sigma bond. So I think that was 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 sigma bonds. Again, every single bond is a sigma bond. Every double bond and every triple bond has 1 sigma bond in it. The additional bonds in a triple bond and a double bond, those bonds are classified as pi bonds. So in a triple bond, we have 2 more bonds. Those would both be pi. And in a double bond, we have 1 more bond. That's also a pi bond. So this molecule has 3 pi bonds. And just sort of as a note, we'll write down here, a single bond is a sigma bond. A double bond is a sigma plus a pi, and a triple bond is a sigma and 2 pi's.